Okay, so we are looking at this one. It is a challenge question, and it is a challenge question because we have barium hydroxide is neutralized. Oh, wrong pen again, sorry. Oh, thank you. Neutralized by 29.10 milliliters of 0.300 molar HCl. And then we want to know the KSP of BaOH2. Okay. So what is the first part of this question? What type of problem? Is it a KSP problem, the first part of it? Eventually it's a KSP problem. It's a neutralization, it's a titration. Can you see that? Because we have 29.10 milliliters of HCl. So we have HCl, and it neutralizes 40 milliliters of barium hydroxide. Yes? Whenever you're given, and you're told they neutralize each other, that's going to be a titration type problem. In order to find KSP, wouldn't it be nice to have the solubility? Could we find the if we had the solubility of barium hydroxide, could we find the KSP? You guys are killing me. Okay, if you have solubility, you can find KSP. It is one of the 5 archetypal questions. Yes? Okay, so wouldn't it be nice if we had solubility? Well, what is solubility? Solubility is the concentration of a saturated solution. Yes? Oh, look, I would like to know the concentration of barium hydroxide saturated. So I know the volume and molarity of HCl. I know the volume, but not the molarity of barium hydroxide. And so the first part we're going to do is a titration to find concentration of barium hydroxide. In order to do that, we need a balanced equation between the hydrochloric acid and the barium hydroxide. And if you just treat this like a normal double replacement reaction, even though it's a little more specific, it is a neutralization. Outside ions, that gives us H, and OH will give us H2O. Inside ions, barium and chloride. Barium is 2+, chloride is negative, so that's going to be BaCl2. In terms of balancing this, remember, balance the ions that are in your salt. So we have a 2 on our Cl, so we will need to put a 2 in front of our HCl. And then finally, don't forget that the number of hydrogen has to equal the number of hydroxide, which will also equal the number of waters. Because if we were to write the net ionic equation for this thing, it would look like H plus OH minus gives H2O. And that is a 1:1:1 ratio. So if we look at our hydrogen, we have 2 hydrogens. We have 2 hydroxides. Oh, look, already those are equal. So now we just need to make the water equal as well. So we put a 2. And now we're all balanced. So now that we have a balanced reaction, we can go back and actually do the titration question. I'm going to write out my information over here because I'm kind of like sprawling all over the page right now. Barium hydroxide, we have 40 milliliters and we don't know the molarity. The hydrochloric acid, we have 29.10 milliliters and we know that it is 0.300 molar. And now I can make this a little bit bigger again. There we go, that's better. So we're going to start with our volume, our milliliters of HCl. We are going to convert that into moles of HCl. And because this is a titration, once you have moles of your known substance, and this is our known substance because we know 2 things about it. We know the volume and the molarity. This is our unknown because we are wondering something about it. We're wondering, what is its molarity? Okay, so we're going to take our milliliters and use moles per liter as our conversion factor to get to moles. From there, we're going to use our balanced equation to find the moles of our unknown barium hydroxide. And finally, we want to find the concentration of barium hydroxide, which is our moles per liter. So I'm actually going to just do the calculation up till here because I want to point something out to you guys when we get there. So let's find the moles of barium hydroxide. We're going to start with 29.100. No, I need to convert that into liters. 0.02910 liters times, that of course is moles per liter. And so that gives us 0.300 moles per liter. But anytime I'm doing a titration means I'm working with stoichiometry. And if I'm working with stoichiometry, can I just leave a mole sitting there with nothing after it? No, that would be unwise because I need to write down that that is moles of my HCl. That way I can keep track of what I have. So we've gone from milliliters, we converted it to liters just in our heads, and then we converted that to moles of HCl. To convert that into moles of barium hydroxide, we need to cancel the moles of HCl, and that ratio comes from our balanced equation, which has gone walkabout. It's up here somewhere. Oh, there it is. 2 HCl's for every 1 barium hydroxide. 2 HCl's for every 1 barium hydroxide. And I'm going to do that calculation, 0.02910 times 0.3 divided by 2 equals 4.365 times 10 to the negative 3 moles of barium hydroxide. I want to find the concentration of barium hydroxide, and that is my moles per liter. And this is what I wanted to show you in particular I so often see this, and you're going to tell me why this is wrong. What is wrong with what I have done there? Yes. Pardon me? In a separate, oh, but it's the concentration of BaOH2, so that's okay. And that's my volume of BaOH2. And in fact, I get the right answer if I do this, but you would still lose marks. Why? Yes. I have written an equation on which the two sides are not equal. Yes? Can we agree that this on this side is equal to that? Yes? We did the calculation and that worked out. So that would be like if I said 3 times 4 equals 12. That's correct, yes? And that's what I've done. Now, if I all of a sudden throw this over top of 0.040, that's like if I all of a sudden just decided to divide this by 2 and left the equals sign there. Is it true that 3 times 4 is equal to 12 divided by 2? No, I can't do that and still have that equals sign be true. So I can either do the calculation all in one line, which I have shown you how to do, but I'll do once again, just to remind you, or this calculation actually has to happen on a separate line. I have to say my concentration then of BaOH2 is equal to 4.365 times 10 to the minus 3 moles over 0.0400 liters, and we get 0.1091 molar. Do you want to see it all in one line? I saw a nod. Okay, so all in one line, what it would look like is this. And in fact, I'm going to cheat a little bit, and I'm not even going to convert out of milliliters. I'm just going to leave it as milliliters, and we'll see why that's okay in a moment. I would have I would have 29.10 milliliters times 0.300 moles of HCl per liter times all the same so far, right? 1 mole barium hydroxide for 2 moles HCl. And if I look at what my units are doing so far, I've canceled the liters, but the milli is still there. Okay. I've canceled the moles of HCl. And right now I have moles of barium hydroxide. If I want concentration, I need to have moles over liters. I don't want to do anything to the top because I have what I want on the top. I want moles, I've got moles. So just leave it alone. What I want to do is I want to divide by my volume. So that's going to be 0.0400 liters. Oh, in fact, because I had my first one as milliliters, I should write it as 40.00 milliliters. There we go. So now the milli actually cancels with the milli. And the only things we are left with now as units are moles of barium hydroxide per liter. You could do this same thing in liters. It doesn't matter. I just thought I'd show that extra little, cheat. Not a cheat. It's perfectly good. Okay. Whew. Now, is that what we were looking for in this question? Not quite. No, we wanted the KSP, correct? We have found the solubility because that is the concentration of hydroxide saturated, and look what we just found. We found the concentration of hydroxide saturated. How do we go from solubility to KSP? Well, you want to have ion concentrations. You want to have your solubility equilibrium equation, and you want to have your KSP. Most of the KSP questions, you'll want to have those three things. So even if you don't know what to do, you could say, oh, could I find my ion concentrations? Well, I've got my concentration of barium hydroxide. Could I find the concentration of barium if I know the concentration of barium hydroxide? Sure I could. They are the same because it is a 1-to-1 relation. And so if this is, and I've sort of lost my thing off the screen there, so I'm going to write it down here, 0.1091 molar. This is going to equal the concentration of barium hydroxide, and that's going to be 0.1091 molar. Can I find the concentration of hydroxide? Is it equal to concentration of barium hydroxide? Or is it equal to something else? Yes, 2 times that much. Yes, because we have that little 2 down here. Oh, that was supposed to be a highlight. That did not work. Hello, there we go. We have that little 2 down there, and so we have to multiply by 2. So that is going to be 2 times 0.1091, and that is times 2 equals 0.21825. Write our solubility equilibrium equation. Why am I writing Mg? It's barium. 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 Hydroxide. Ba2 plus aqueous plus 2 OH minus aqueous. And write our KSP expression. Barium times hydroxide squared. Plug them in. 0.1091 and 0.21825 squared. And we get 5.2 times 10 to the -3. And I have no idea if I've done my sig figs correctly. I would need to go back and take a look at that. Let's see. Sig figs, I had, 3 sig figs. Oh, so that would be 5.020. There we go. That's a tricky question. You're not going to get one like that on the quiz, okay? Just so you know. But it was good practice on both titration and KSP, yes? And those are the kind of questions you can expect all the time in university because they don't do things one at a time. Oh man. Okay, let's see. What did we have next? 3.2G, number 6. Ooh, another challenge question. Oh, this is just like the last one. This is actually exactly like the last one. So should we do it or should I just leave it for you to try? Leave it for you to try? I'm going to leave it for you to try. You'll be doing it. It's just exactly the same. You'll do the titration first, and then you'll find the concentration of hydroxide, which is the same as concentration of AgOH, and then you'll use that as the solubility to find your KSP for AgOH. And like I said, you're not going to get one like this specifically on the quiz, but it is good practice. Yes? On the test? No, probably not. Back in the olden days when there were scholarship exams, like way back when, in the early 2000s, that would have been the kind of question you'd find on a scholarship exam, but not on a regular one. Okay. And 3.2I, number 2, 6, and 7. Number 2, number 6, and number 7. Can I do number 7 first? Because I want you fresh for this one, or at least sort of fresh. And the reason I want you sort of fresh for this one is because number 7 involves a procedure that I wanted to go over with you today anyway. Yes? So if you wanted to experimentally find what the KSP is for a certain substance, this is one way you could do it. First thing you would do is you would create a saturated solution of, in this case, Mg2F. So create a saturated solution of MgF2. How would you do that? Dump and stir. Dump in some MgF2, stir it, okay? Dump and stir method. Now, second thing we need to do is that we need to take a sample of that saturated solution and figure out how much solid there is in it. What could you do to the solution to figure out how much solid there is in it? If I gave you a glass of salt water and I said, what's the mass of salt in here? How could you figure out the mass of salt? Yes? You could evaporate it. Yes? So let's assume that I've got some saturated MgF2 and I'm going to put some of it into a beaker. Yes, and then I'm going to evaporate it. Now the only problem with this is in the dump and stir method, what do you have left over? You dump and you stir. How do you know you're saturated? Because there's some solid left, yes? If you then evaporate it, you will be measuring the mass of not only the dissolved stuff, but also the undissolved stuff, yes? So let us filter out the extra undissolved MgF2. So filter out undissolved MgF2. Third thing you're going to do is you're going to evaporate it, but you need to know what volume it's in. So you're going to measure out a particular volume, whatever you want. Okay, measure a specific volume of the solution. Now we know the liters, yes. And place it in a beaker. Evaporate the solution. And find the mass of the solid remaining. And that's going to give you your grams. And if you have grams and you have liters, you also have moles per liter, yes? And if you have moles per liter, you have solubility. And if you have solubility, you can find your ion concentrations, you can write an SCE, you can do a KSP, and boom, Bob's your uncle. Yes? And if anyone's like, what the heck is Bob's your uncle? It means, and there it is. And there you go. It's one of those weird British expressions. All right, my question to you is, I have left out something very important in here. How am I going to figure out the mass of the solid remaining? When I evaporate, have you guys ever seen like salt water that has evaporated? What does it leave behind? You've never seen that? Not like on a beach or anything? No? Okay. Okay, so it just looks kind of crusty. Okay, so you would have this glass of water and the water would be gone, and now there would be like a salt crust on the sides. How are you going to find the mass of that solid? Because it's stuck to the beaker now. How are you going to find the mass of that solid? Yes? You are going to have to subtract the mass of the beaker, which means that up here, step 2A, you're going to have to measure the mass of the beaker, yes? Because otherwise you can't subtract it. Why can't I just weigh some other beaker and subtract the mass of that beaker? Like, what if I forgot to weigh the mass of the beaker? And I'm like, oh, I'll just weigh some other beaker. Yeah? Beakers have different weights. The chances of them actually weighing the same is very, very small. Okay, so that's a useless sort of a thing to do because you'll just end up with error all over the place. So we have to measure the mass of the beaker, and we find the mass of the solid remaining, which is equal to the mass of the beaker plus the solid minus the mass of the beaker. And from there, we have grams per liter, and from there we can find moles per liter, and from there we can find KSP, because this is all of a saturated solution, yes? So that is what is actually happening in this question. And I will make sure that these notes are posted, but I can give you a minute to finish writing if you would like. Anyone want to finish writing? No? Okay, then I'm just going to go back here and we're going to take a look at our actual data. In this case, we didn't use a beaker, we used an evaporating dish. Yes? And so then we had the evaporating dish and the magnesium, and then we also have the volume of the saturated magnesium fluoride that we used. What am I going to have to do with these two numbers? Tell your partner, what will I have to do with those two numbers? Yes. Yeah, we're going to subtract massive evaporating dish from the other mass. I'm not going to write down the mass of the evaporating dish plus MgF2 because it's just too big to fit right in there. Okay, so we're going to find the mass of MgF2. That's going to be the mass of the evaporating dish plus MgF2, that entire mass, minus the mass of the evaporating dish. So that is 78.5434 grams minus 78.5418 grams. And we get 0.0016 grams. This is subtraction. How many sig figs did we start with here? How many sig figs there? 6 sig figs. How many here? 6 sig figs. How many should I have in my answer? I should have 4 decimal places, because remember, when you're subtracting, you go to the least number of decimal places, and so I have 4 decimal places, and so now, because it is subtraction, I end up with only 2 sig figs. So my answer cannot have more than 2 sig figs, okay? All right, so that gives me my mass. Now we can find our concentration of MgF2. We have 0.016 grams in what volume? Let's see. Ooh, in 100 milliliters. So 0.100 liters. But I don't want grams per liter, do I? I want moles per liter. So MgF2, what is the molar mass of magnesium? 24.3. 24.3 plus 19 times 2. 62.3 grams per 1 mole. 0.0. Ooh, I forgot a 0. Another 0 in there. 0.0016. 0.0016 divide by 0.1 divide by 62.3 is 2.568 times 10 to the negative 4 molar. What three things would I probably want to use in order to find the KSP? Yeah? And this is where, once again, even though the first part of this question was a little bit complicated, we go back again to basics. Find your ion concentrations. So, concentration of magnesium, oh, that's easy. That's the same as the concentration of magnesium fluoride. Well, that's puzzling. Now, do we want to go through the whole process of this? Or do we want to just be like, okay, we're good now? We're good now? If you want to see the rest of it, I think I did the rest of it in my other block, and I recorded that, so you're welcome to tune in, and I'm going to post the worked answer, although the worked answer is in the key as well, so yeah. Okay, so that was number 6. And then number 7, we need to calculate the silver, or was it 7? No, it was numbers 6 and 2. Okay, let's start with 2. Here we go. The maximum mass of MgOH2 that will dissolve in 150 milliliters of water. The maximum mass is going to give us a what kind of solution? That's going to be a saturated solution. So if I can find my moles per liter, yes, I could convert that into my grams per liter, which I could then convert into grams. Yes, because I know my volume. Or I could take my liters and I could then convert it into moles using the moles per liter, and I could convert that into grams. But the basic idea is that in order to solve this problem, I need to know my moles per liter of a saturated solution. And what is the moles per liter of a saturated solution? What do we call that? That is the solubility. So what this question is really asking you, it's asking you in a roundabout fashion, what is the solubility of MgOH2? And if you have a question that says, what is the solubility? What's the first thing that you're going to do? You're going to do your let statement. Let X be the solubility of MgOH2. And from there, I'm going to take us up here now. We want, once again, oh, guess what? Ion concentrations. Yes. And we want our SEE, and we want our KSP. In this case, I'm going to write my SEE first, because that way I can write my X's underneath. So MgOH2 equilibrium with Mg2 plus 2OH minus, aqueous. Aqueous, solid. Here are my concentrations. I said that X is the solubility of MgOH2, and that means magnesium will be X, but hydroxide will be 2X. Now you can write the KSP. KSP is concentration of magnesium times concentration of hydroxide squared, which is equal to X times 2X all squared, which is equal to X times 4X squared, because we squared that whole thing, and then that's equal to 4X cubed. And from there, we need to have a KSP to solve this. I don't think the question gave us one. Let's look and see. Where did it go? Number 2. No, it didn't. Where will we go? Data booklet. Magnesium hydroxide. Where are you? 5.6 times 10 to the minus 12. 5.6 times 10 to the minus 12. And now I'm going to solve for x cubed, which is equal to 5.6 times 10 to the minus 12 divided by 4. 5.6 times 10 to the minus 12 divided by 4 is 1.4 times 10 to the minus 12, and then x will be the cube root of that. (1.12) times 10 to the minus 4, and that is molar, and that is the concentration of magnesium hydroxide. The question wanted to know how many grams of MgOH2 are in 150 mils of a saturated solution. I think it actually said how many are needed to saturate the solution, but that's essentially what it's saying, yes? So we have grams of MgOH2. Let us start with our milliliters. 0.150 liters times, now we know we can cancel liters and find moles because we know that here. That of course is moles per liter. 1.12 times 10 to the minus 4 moles per liter. And then we need the mass of magnesium hydroxide, so 2 times 16 plus 2 plus 24.3 equals 58.3 grams per mole. (9.79 times 10 to the negative 4). In a question like that, it's probably not like the math itself that's hard. It's just like sorting out that you need to find the solubility of it in order to find the grams of it. You know what I mean? So yeah, that's the tricky part, is figuring out what do I need to know in order to actually answer the question. I actually need to know the solubility. All right, and one more. Number 6. The mass of Na2CO3 that must be added. Okay, so I'm just going to write this down. Actually, maybe I'll get a new copy of this. Let's try that. There we go. Yeah, okay. So we want the maximum mass oh no, we wanted number 6. That's just the one we just did. Number 6, the mass of we want the mass of Na2CO3 added to 2.50 liters of MgCl2 to just start precipitation. Okay, just start precipitation. That means that this is you know 2 of the things in KSP, solve for the 3rd one. So if that's the case, well, we always need to start then with our solubility equilibrium equation. Ooh, but we have two compounds here. Oh dear. Am I going to be writing, here, I'm going to give you a few choices, and you see what you think about them. What do we think of those two choices? Anyone thinking those are terrible, stupid choices? Those are terrible, horrible choices. They're both soluble. They're both completely soluble. When I write a solubility equilibrium expression, and when I have two compounds, what do I need to do before I write my solubility equilibrium equation? I need to identify the precipitate. So if you've got two compounds, don't be like, oh, I'm just going to pick one and write an equation. You need to identify the precipitate first. And so it's certainly not going to be the one with sodium, so it won't be sodium chloride. That means it has to be MgCO3. And now we can write a reasonable solubility equilibrium equation. Mg plus CO3 2 minus aqueous. Whew. Okay, where did we get to? There we are, and then we can do our KSP. Mg2 plus CO3 2 minus. And remember, if you're just starting precipitation, or if it's just barely beginning precipitation, or the maximum you can have without a precipitate forming, you will know two of the things in KSP, and you will be solving for the third. Oh, I must have not written something down. Number 6. Ooh, 2.50 liters of 0.00085. It's like I'm missing a piece of information. I don't have two pieces of information. So I know the concentration of magnesium, yes? That's given to me in the question. So I can just plug that in right here. 0.00085. I want the amount of CO3 or NaCO3. So that is my unknown. So I'm just going to leave it like that. That means that my KSP has to be a known value. And if it's not given to me in the question, which it is not, I don't think, then I need to go and look it up. Magnesium carbonate. 6.8 times 10 to the negative 6. 6.8 times 10 to the negative 6. Solving for carbonate. CO3 2 minus is going to be 6.8 times 10 to the negative 6 divided by 0.00085. 6.8 times 10 to the negative 6 divided by 0.00085 equals 8 times 10 to the negative 3 molar. But that is not what I want. I want the maximum, or sorry, the mass of Na2CO3 in 2.5 liters with that concentration. Yes? So, mass of Na2CO3. I'm going to start with my 2.5 liters, convert that into moles. 8 times 10 to the negative 3 moles per liter times 23 times 2 plus 12 plus 3 times 16 is 106. 106.0 grams per mole times 8 E3 negative times 2.5 equals 2.12 grams into CO3. Is good. And remember, if you're lost and you're like, I don't know what this question is asking me for, try finding some ion concentrations, try writing the solubility equilibrium expression. If you have two things, identify the precipitate, write a KSP expression. You might just find that by the time you've done all of those things, oh, I guess I could solve for something. You know what I mean? So, and if not, even if you don't, you've already gotten like at least 1.5 marks out of whatever it is. Yes? So that is a fine and wondrous thing. That's all you guys asked for. So do you want to just have a little work time or rest time or something time? Okay, because I mean, honestly, I went to the bell in period 2, so I didn't do anything else with them. So you can just do review. If you're feeling good about the calculations, you can work on the overall review. If not, you can just leave that till tomorrow for after the quiz. Okie dokie. Oh yeah, no, that's fine. I have a different tape. That was like my favorite tape. Yeah, I have another one, and I was using it in it. So I'm wondering if I like hit it somewhere. I will be here tomorrow during flex, just in case anyone wants to drop by. Good for you. That's tough. Yeah. Hello, Gavin. Thank you. Oh my God. Okay.
Can you believe this guy? I can't believe he did that.
Hello. So, my lovely students, we have for you, I'm going to give it to you today, although you probably won't use it today, you'll probably use it tomorrow after the quiz. There is a review here of all of solubility, okay? So why don't you come pick one up? Because today I'm just going to go over questions, and if I'm going over a question that you already understand, you might be bored and want something else to do, okay? Oh, and I'm not gonna fall asleep on you, I promise. When's your test? I have to look on a calendar. I don't know what day of the week it is, or what date it is. So what you guys are going to do right now is look through your stuff that you worked on over the weekend, and you're going to let me know which questions you would like to go over. Huh? Yes, you may. Oh my God. Okay. Oh. December 8th and 9th. Although we're going to be like done, we're done as of tomorrow, essentially. We have some lab stuff and whatever. But, oh yes, we are. What do you mean we can't really start a new unit? Of course we're going to start a new unit. It's either that or I test you on Friday. Uh-huh. We're just going to we're going to press pause for a week? That doesn't happen. We're not going to finish this course anyway. We can't press pause for a week or we won't finish like 2 units instead of just 1 unit. You're like, how can I make this happen? But it's not going to. Okay. So, let's see. Turn that on. I recorded. Oh, am I still recording? Let's see. Oh yeah, I'm just still going here. Maybe I'll press